2, 1. Exponential functions test. When you're watching these videos, the tests that I make are always hopefully a little bit challenging. So once again, you can download this test. You can just go to the show notes, click on the link, get the actual PDF file, solve it for yourself, and then come back and then see, because I go over the entire test and the solutions. There are 5 questions to this one, and this is the exponential functions test, okay? So which is kind of for grade 11s, but it can honestly be for anyone who wants to see, how well they remember these. Okay, so let's get started. Question 1. For the following set of 3 functions, state, so we have a restriction here, so x is greater than 0. If they are decaying or growing, do so without graphing and state why. This is a pretty interesting question. It's not a very hard one, and you should be able to grasp it rather quickly if you understand exponential functions and which ones decay and then which ones grow. Now, I have 3 functions here, so I have f1, f2, and then f3. I'm using different independent variables, so x, n, and t, but that doesn't really matter. So for the first one that we have, so within here, what tells us if a function is decaying or growing if it's an exponential? Well, so if you recall, so the structure is typically something like this, right? Where we have an exponent on our base b, and depending on what b is, so 2 cases can happen. B can be greater than 1. Now, these functions are actually growing in the case that your exponent that you have, and in this case we do have our exponent, so our exponent here is just x. And so these functions are going to blow up on us, so they're going to be exponential growth functions if that's the case. So for f1, this one right here is going to be an exponential growth because the base, which is 3.1, is bigger than 1. Now f2, so if I take a look at that one, so this one right here, notice once again, so for this case, our b, which is 1 plus 0.1, which really is just 1.1, again is greater than 1. So for that second function, this one is also growing. For the third function that we have, and that's this one, so in this case, what is our base? Our base is 0.45. Now, what do we know? We know that for this instance, if b is between 1 and 0, then those functions are actually decaying. So they're going to be slowly decaying towards 0. So for this one, it's going to decay. And the reasons, if this was on a test, you can compare it to your original and then state the reason based on your base. So between 0 and 1, it starts to decay. If it's greater than 1, it starts to exponentially grow. That's question 1. Question 2, this one is actually my favorite. And it's all about transformations and really understanding these exponential functions, plus what transformations do to our parent functions. We have this rather crazy looking function right here, so f of x, and it's asking us a slew of questions. So it's asking us, what would be the parent function of this? Sketch f of x. Now notice sketch by hand, so not plot it, at least not yet. Find the domain, find the range, find the y-intercept. They actually don't ask us for the x-intercept, but I'll do it anyways. What is the asymptote for this function? So remember, exponential functions do have typically an asymptote if they're just exponential on their own. Then the last one is plot f of x by using a graphing tool and then compare it to your sketch. So that's just kind of, I know on a test might be strange if, most of the time you may not have that part f on a test. You might have a to e, where you have to kind of do it by hand. But here, let's actually graph it as well so that we can compare and then talk about this function. Okay, so I'm going to take this as it is, and I'm actually going to answer all the questions kind of one by one, not necessarily in order for this. So I have -3, and then in brackets 2 it is to the negative. Notice, first thing that I'm going to do is I'm going to factor out that negative 2 because I want to place it in the form of our transformations. All right, so I'm going to do something like this. Now, remember that transformations, what you have is, if you have a parent function, now for us, what is the parent function? Well, our parent function, the regular function, which is, b of x, or b to the x, well, for us, our parent function is 2 to the x. That's what this is. So that's what you would have, and you can see that directly from here. Now, our transformations that we have, remember, so this is basically what we're trying to see is, this, if you remember, for transformations A, and then we had, our functions. So we had, some f and then d, okay, x minus h plus our k, all right? And what we wanted to be able to see is, what is our a, what is our d, what is our h, what is our k, and now what do these a, d, h, and k do to our parent function, right? So if this is, now I'm going to assume I'm using f multiple times, which isn't really the greatest, but this is my parent function, so 2 to the x. And now I can slowly, okay, one by one, see first, what will A do to it? What will D do to it? And then the H and the K, those ones are just actually kind of shifting it, right? Up or down, left or right. Okay, so the H and the K just kind of shifts my actual plot. But the A and the D, those ones either compress or stretch in the Y direction or in the X direction, and also depending if they're both positive or negative. If they're negative, then there is a reflection either in the X, okay, or in the Y. So that is really testing your ability to understand these transformations as a function. So first off, what I'm going to do is, let's graph this one. Now again, it says a sketch, so it's not going to be perfect. So that's okay. But we're going to slowly try to get it as perfect as we possibly can. So I'm going to, maybe I should shift this in here. All right, so this is my, let's say this is my X. Okay, this is my Y. And I'm going to be trying to sketch. Now, 2 to the X. How does that look like? That is something that you should know. This exponentially grows. It has an asymptote basically at 0 in this direction. And then it just starts to skyrocket in this way. All right, so it crosses right here. Okay, so this would happen at x is equal to 0, which would give me a 1. And now what I'm going to do is I'm going to one by one adjust based on the values of this particular A, D, H, and K. And if you're sketching, do it one by one. Don't be brave and try to do it all together. Okay, just do it one by one. That's kind of the beauty of these transformations with exponentials and some other parent functions as well that you probably have studied in grade 11. So first of all, what is A? So if I take this, I'm going to map this out. I'm going to copy it for myself. I'm going to bring it right here, paste it. And I'm going to, okay, match it, okay, with the transformation. My A, this is my A, so it's -3. Okay, now I'm going to take my parent function. Now, this is D, so D is going to be -2. It's going to be x minus 2, so that 2 is my H, and then it's +3, which is my K. So notice that's what is matched. And now, let's do it. So first, let's work with this. Now, what do we know about that A? That A either compresses or stretches in the Y. And if you recall, if the magnitude, so if the magnitude within here, the magnitude is basically, if it's greater than 1, then there is a stretch in the Y. So what you should see, so this, I'm going to kind of just jot it down. Okay, so maybe, let's see, okay, this way. I'm going to take that green. So what's going to happen is it's going to stretch this kind of and make it faster. Okay, so it's going to stretch it out further. Okay, that's the stretch. So it's like taking these and then stretching them out. Now, if it was between, if the magnitude of the A was between 0 and 1, it would compress it down. It would bring it down. That's what happens in there. Now, the negative, okay, on its own, so this particular negative that I have in here, what does that negative do? That negative does a reflection in the X. That's what that does. So it's going to reflect it in the X. Before I actually reflect it, okay, in the X, I'm going to do that reflection in the X after I see what the actual compression or stretching is done by this D, okay, this -2, which is 2 in general. All right, so it stretches in the Y, so it pulls it out. Now, this D that I have in here, what does that do? So what that does, let me go back in here. So the magnitude of that, if it is greater than 1, now it's working in the X. So it's compressing or stretching in the X. So it's either compressing it, okay, or stretching it out. So now it does the kind of the opposite. So notice, remember, this in the Y was a stretch that way. Now, when it is greater than 1 in the X, it's actually a compression. So it actually almost further stretches it out in the Y. So here we're going to get a compression. So a compression, so in this case, this was a stretch, kind of like that. But this is a compression in the X. So if I wanted, so what's going to happen to this is now going to look even more kind of compressed in this way. So it's going to even further kind of go in this direction. So it's going to get even more compressed. All right, except it's in the X, so it's almost like stretching it out even further in the Y. So that's the second thing. Now what I can do is now I can check, and now I'm going to do the actual reflections. So my reflection here, this one, the -3, that means it reflects it in the X. So I'm going to do that. So if it reflected it in the X, so this brown, okay, so that you see there, so it's going to get reflected in the X. So it's going to look identical, but it's going to get reflected like that. Okay, so it's supposed to look kind of the same, okay, except it gets reflected back. And now from the D, notice it's also negative. So that means it gets reflected in the Y. So in the Y, so what's going to happen is, so it's going to look, okay, kind of the same, except, okay, it's going to now get reflected in the Y. So it's going to look like that. Yeah, so this is what I have so far. Now my H and my K. My H and my K that I have, so right here, my H and my K. So my H and K. So these are the two shifts. The H, okay, so shifts it in the X by 2, and the K shifts it in the Y by 3. So meaning this graph, okay, right here, so maybe now I'll highlight it here. So that actual plot, okay, that I have in there is going to move to the right by 2 and move up by 3. So that's what I want to see. Okay, so if it's going to move, so if I'm going to just move it to the right, I'm running out of colors here, but that's okay. So it's going to move to the right, so it's going to shift this over, okay, even further. I don't know, I mean, it's kind of hard to stretch, I mean, to plot in here, but it's going to look kind of like this, and now it's going to move it up. So it's going to get moved up by 3, so I guess it's going to look probably something like that, and it's going to start to go in this direction. And this is my plot right there. So I'm going to actually remove all of these, okay, so that it's just kind of clean. And I'm just going to leave my parent, okay? So that's what it would look like. That's what we're hoping for. Now, what are these, intersecting points? And then here, we will have an asymptote of some kind. So now we want to also be able to find that asymptote. What is it going to be approaching there? And then maybe we can find the x and the y intercepts, because it does ask us for that. So that's the sketch. So we have so far answered what would be the parent. Okay, so we know what the parent is. It's 2 to the x. We sketched it by hand by using transformations. What is the domain? Okay, the domain. Well, the domain for this, so for the x, so the domain, notice, so for this, it's basically x belongs to all real, because we don't have any restrictions at all in here. So it can be for any x, going left to right. Your range, well, your range, so your y is restricted actually. Now, it's going to be y, I guess, less than. Now, we don't know exactly what that asymptote is. So I'm going to put a question mark here for now. But we can probably figure that out rather quickly. So if you take the original, so I'm going to just highlight this in here. Let me remove this. So if you're looking here, this is your function. We know that, so it's going to be approaching something. Now, what is it approaching? That means we want to be able to see what happens as x gets bigger and bigger and bigger. Now, if x gets bigger and bigger and bigger, what you should notice is that what happens to this term right here? If x gets bigger and bigger and bigger and bigger, it basically approaches 0. That's what will happen. Now, why does that happen? So what this is, now here is where, you know, your idea and understanding of exponential is. So what does this mean? This is 2 to the negative. I'm going to bring this negative 2 back. So it's to the x multiplied by 2 to the 4, right? So this is what that is, right? Because the same base. So notice negative 2x plus 4 is the same thing as what I have written there. So what does this equal? So this right here. So we have negative 3, okay, multiplied by 2 to the 4. And I'm going to bring this, okay, because notice it has a negative exponent. So this is 2 to the x. So as x gets bigger and bigger and bigger, these things just stay fixed. They're just some number. And this, in the denominator, as x gets bigger and bigger, goes into infinity. So that number overall, so this approaches 0, basically, or, you know, negative from the negative kind of bottom side, and which means that we just have this plus 3. So that asymptote right here must happen at y is equal to 3. So for our domain, this means that the question mark, this has to be less than 3. So it can be anything, but it has to be less than 3. It never crosses that 3. It's going to be approaching it. And that's, again, just understanding these exponentials that we have. Now it says find the y-intercept. Okay, well, finding the y-intercept, so for this, I'm going to copy this down. Copy. Y-intercept. Well, y-intercept happens, okay, at f at 0, right? So the y-intercept that we have, if I substitute, so it's going to be negative 3, 2 to the negative 2. Okay, this is 0, right? Minus 2 plus 3. We can compute this. Negative 3, this is going to be times 2 to the 4 plus 3. Okay, so negative 3, 2 to the 4 is 16 plus 3. So is that what it is? So this is negative 48 plus 3, which is negative 45. So that's my y-intercept. So my y-intercept is, so 0, so x is at 0, this is negative 45. If I go back here, so this point is actually negative 45. That's where that crosses. Now, can we find our x-intercept. This might be a little bit harder. This question didn't ask it, but let me do it anyways. How would you find that? That happens when y is equal to 0, right? So if I took the same thing, let me paste it. So here, this is when y is equal to 0. Now we're supposed to solve for x. Well, let's see if we can do that. So we have negative. Okay, so I'm going to bring this over on the other side. So I'm just, manipulating this equation by what we have learned already in the past. I'm going to have this. Let me not skip too many steps here. Okay. Now I can divide by negative 3 on both sides. So this negative 3 divided by negative 3, that's just 1. So that means this becomes 1 equals 2. This is now 2 to the negative 2x. Let me distribute that back in there. So that's what I have there, which equals, 2 to the negative 2x. That 4, so this is the same thing as, times 2 to the 4. This is 1. Okay, this is solvable. So now divide this by 2 to the 4 on both sides, right? So this 2 to the 4 over this 2 to the 4, so that's gone. Now this right here, this is where your exponent rules come into play. So this is 2 to the negative 4 is equal to 2 to the negative 2x. Hey, wait a minute. They have the same base right here. So if they have the same base, then we can actually solve for that x. All you need to solve for is just this. So so it's asking me negative 4 basically is equal to negative 2x. Well, I can solve that. Divide by negative 2 on both sides, and you will get negative 4 over negative 2, which is just 2. So it looks like, so that's my x-intercept. So that point right there happens at 2, at x is equal to 2. So we know quite a lot without actually even plotting anything. Now, what else do they ask us? So we found that. What is the asymptote? We found that, because that's y is equal to 3. Okay, now let's plot it. So I'm going to use Desmos for this, and then see if we were actually correct. Okay, so in this plot, so does it kind of look like that, and does it cross through negative 45 and 2? Let's check it out. All right, so here it is. Okay, let's see. So I put the variables a, d, h, and k because I just wanted to show you, okay, so what happens. So we're going to go one by one. So what did we say? Okay, so our parent function is 2 to the x, which is currently plotted right there. Now, if I set a to, because it's negative 3, right? It was negative 3. So I'm going to set it to 3 first. And actually, you know what I'll do is I'll actually, write, say, g of x, so that we have our parent to look at, 2 to the x. Well, I don't want this to be red as well. How do I change the color here? Okay, let me see. So here's our parent. Okay, and I'm going to plot this. So notice again, so here is 1. Okay, so they're basically on top of each other. That's what I have. Now, when I move this to 3, we said that it would stretch it in the y, right? And it did, right? And notice it pulled it back. Now, if d, so now notice d was negative 2. So I'm just going to put it at 2. What was that supposed to do? Supposed to squish it back in even further. So let's see if that's what actually will happen. Yes, it did. Squeezed it even further in like that. Now, notice that I was off, okay, there because it squeezes it from both sides. So it's very, narrow at the bottom, and then it just really explodes up. So far, so good. Now what we want to see, okay, if this was negative, so that means it should flip over in the x. There you have it. Now, d, this was also negative. So that means that red should now flip into Y, okay? It should just flip like a mirror image there. There you have it. And it did that. And now, so my H, so our H was 2. So it should shift it to the right by 2. And there you have it. And it should, and my K was 3, so it means it should go up by 3. And there you have it. And notice the asymptote indeed, okay, is basically going closer and closer to 3. I mean, it rounds it for us. So eventually, you know, Desmos is going to round it to 3, but it just gets closer. Now, we wanted to see, so notice the x-intercept, notice 2. So we got that right. Now my y-intercept was supposed to be 45. And yep, there you go, 0 and negative 45. So thumbs up, okay? So we did a pretty good job in terms of sketching it out. And hopefully, you know, you found this useful. This was the hardest question for sure on this test, but the most rewarding in terms of learning experience. Question 3 is an application question. So it says a virus has infected 12 people in a major city. The infection rate for the virus is 7% daily. And I guess we're going to try to model this in terms of an exponential function. So it has 4 parts. Construct a function for this scenario. State what your independent and dependent variables are. How many people would be infected in 100 days if this rate of infection continued? You know, sketch the function and then graph the function and compare to your sketch. Okay, so let's try it. Now, we have, so this is for part A. What do we know? Well, the infection rate for the virus is 7%. So this is kind of exponential growth. So let's go back. Now we have a population. So I'm going to say P of N, I guess, is equal to, what do we start? We're starting at 12. And this is going to have, so 1 plus, so notice 7%, okay, is 0.07. And this is to the n. All right, so this is what I have for my exponential growth function. Now, my independent variable is n. So that's the number of infected people. So that's what you would say for that. And my dependent variable is, n. So here, let's maybe state it. So n, which is my independent, so this is time, okay, and in particular, number of days. That's independent. My dependent variable is p, which is the population. So p, okay, of n, so this is the number of infected people. There you have it. Infected. All right, so people after, you know, certain amount of days. That's part A. How many people would be infected after 100 days? Okay, so that's for part B. So I can substitute 100 in here. I can find out exactly what that is. Clear this 12 times 1.07 to the 100. All right, so that's a lot of people. Let's round this because we don't want to cut anybody in half there. So that's approximately how many people would be infected. So over 10,000. It grows pretty quick. Now sketch the function. All right, so sketching the function. This one is much easier than what we had. Okay, so this is my n. This is, you know, my p. I guess, should kind of correct this, shift it over a little bit, because it can't be negative, right? So we're n, so the number of days from the infections is, you know, 0 or greater than 0. So at here, what do we have? We're starting at 12. So this would have been 12, and this just skyrockets up. All right, so this is going to skyrocket upwards. Okay, and that's what the actual sketch would have looked like. graph the function and compare to your sketch. I mean, we certainly can do that. So let me pull up decimals here. Let me close these. So we have P of n is equal to, we started with 12, and this was 1.07 to the n. Okay, there you have it. Okay, now let's put the restriction in there. So we'll see how that looks like. And indeed, so it really blows up. I want to here get to the 100. Okay, so there you have it. If I go in here, let's see, we get there. 200. We're gonna get there. All right, so there's about 100 there. You get the point. Okay, so it's about 10,400 something. I can't remember what that number was. So it certainly looks like our sketch, just kind of blows up right away. That was question 3. Here's question 4. So Jonathan invested $10,000 at age 15 in the stock market, which has been growing at 9.5% annually. So basically per year, there's that much growth. So again, this is an exponential growth. And we have R, so our rate is 9.5%. I guess this is going to be in years. And so for how long, I guess we have to see. So construct a function. Okay, so let's do that first. So if we're going to construct a function, now this is money. So whatever, you want to call it. So I'm going to actually, I'll try to give you the formula as it typically is given in money. So I'll say FV, which is the future value, right? So I'm going to say this is the future value of our money. Okay, so that's going to be our function. We're starting with $10,000. So that's my A. 1 plus, now here's my growth. So that's my R. So this is, remember, it's coming from A, 1 plus R, okay, to the, well, in this case, to the N, because it's growth. So that's why it's plus. So then I need N in here. State what your independent and dependent. Okay, so my N, my independent variable is number of years, because it's annually. And my dependent variable is future value, so money in the future. So this is future value of money. So that's what that would be. Part B, so how much money after 25 years? All right, well, let's see. I don't know how much money they'll have. 1, 2, 3 times. It's going to be 1.095 to the exponent of 25. So I'm sure it's going to be a lot. It's almost 100 grand. So that's the future value at 25 years. It's going to be, you can substitute all the values. You can check it out for yourself. This one, it is money, so I'm going to round to the cent, so it's 64 cents. That's quite a bit of money that you have. I mean, it's almost 10 times as much as you started with. So this is great so far. Part C, graph the function and check when the investment would reach 1 million. Okay, well, let's see how many years after 25, it's going to actually reach 1 million. So that's my graph, and we wanted 1 million. Okay, so 1 million. There we go. Okay, so notice here's after about 25 years, so it's getting closer to that, and then it really starts to explode. Over 200, it just takes about another 8 years, and then it just keeps going. Now 1 million, I guess, there we go, it's going to be somewhere around 50 years. okay? But that's, remember, that's just putting in 10,000 at the start and then not actually investing any more money. If you kept investing, would have been more. But that's an exponential, so this is another great example and application of exponential functions. So that's what we had there. Question 5. So an AA battery source starts with approximately 14,000 joules of energy. The half-life of the battery while in use has been given as 3.5 hours. All right, so this, when we see half-life, that means it's exponential decay, right? So we know that the rate is 50%. Okay, so now let's take a look. And now it says, so it's 50% every 3.5 hours. So construct a function for this scenario. All right. So if you're working this out, you can construct, so there's two ways. Because we have half-life, so that means you're either going to do it in time, t, or you're going to do it in half-life periods. So you can I'm going to provide you both. So this is energy. So I'm going to say E of N is equal to, so it starts with 14,000. Now we know, so half-life, so that means it's 1 minus a half, or 1 minus 50%, which gives us 1/2. And then this would have been N. Okay, so that is if you're actually only doing it in half-life periods. If you want the function to be with respect to time, so it's going to look identical, but remember that instead of N, we're going to have T divided by, okay, in this case, it's going to be 3.5. And I'm going to assume that T here, so this is time in hours. All right, so that's what that is. And so that's my independent variable for that one. The N is, if you want to call N and define it, that would be the number of half-life periods. The capital E, which I used, okay, is basically I used it for energy. Okay, so my dependent, so here this is energy because they're doing it in joules. So how much energy would the battery hold after 12 hours? Okay, so B, so I want to know how much after 12 hours. So I have this much at the start. So this is 12 divided by 3.5 equals. So let's plug that in. So we have 14, 1, 2, 3 multiplied by, and I guess it's a half. I'm just going to put 0.5 instead of 1/2 to the exponent. Now my exponent, here I'm going to put it in brackets, 12 divided by 3.5 and equals. All right, so how much would that be? So we have only 1300. It didn't tell us to round. Oh no, it did. Round to the whole number. Okay, so well, that's to the whole number. So from 14,000 we went down after 12 hours to only having, and this would be joules, 1,300 as our answer. So that's how much energy we would have left over. So we lost quite a lot already. Okay, so that's part B. Now, how many half-life periods would it take to drain the battery to 100 joules? Ooh, that's interesting. Okay, let's try to graph that so that we can see it. Because what they're asking us is, okay, kind of 100 joules, or less, I guess, where we're starting from that. And we want to know, so T over 3.5. So how many half-life periods? Okay, so if they want to know half-life periods, so I'm going to keep it in N instead of T. So how many half-life periods would it take? Okay, well, let's try to see. I'm going to use it by graphing. Now, when you start going into the next chapter and you start utilizing logs, you can actually solve this equation. But for now, I'm just going to use the graph. And it's going to be neat because I want to kind of see the graph. Okay, so there we have it. Now they said under 100 joules, right? So we want to get to that point. So how long would it take to get to 100 joules? So notice, so it's 3,000. So I'm just kind of going to go over and over. Actually, let me plot here. Y is equal to 100, right? Because we want to be able to have that intersection point. So we want to be able to see that intersection point right there. Okay, so it's going to take about 7.13 approximately half-life periods. If you want to know how much time that is, right? So don't forget that you can use the formula and multiply it by 3.5 hours because that's how long it takes, okay, to reduce it by half. And that's it, okay? So there you have it. So this was an awesome test. I think if you are able to solve these, you're going to be extremely well prepared for understanding these exponential functions when you're learning it in school, typically grade 11, all right? Maybe even further on in advanced functions in grade 12 or onwards. All right, thanks for watching, everyone. Okay, cheers. Bye.